Okay, and our final talk in the oral session this morning will be from Josh Schiffrin from Carnegie Mellon. And the title of his talk will be Macroscopic Quantum Tunneling in a Damped Josephson Junction Coupled to a Nanomechanical Resonator.
Hi, I'm Joshua Schiffrin. I go to school at Carnegie Mellon University, and this summer I've been working with Yasser Halal and Dr. Shreves. So first of all, in brief, what is a Josephson junction? Basically, it's a layered device where you have two superconducting layers with a non-superconducting layer in between. And even though there's that non-superconducting layer there, if you run a bias current IB through the junction, you can still go through without any resistance, as long as that bias current is less than a certain critical current IC. And there's a famous model of a Josephson junction which says that it's basically three current channels, one a capacitive channel, one a resistive channel, and one the supercurrent channel. And using this model, you can find an equation for phi, which is the phase difference between the wave functions in the two superconductors, which looks like this down here. And that equation is equivalent to the equation of a particle which is under the influence of a certain potential, which we call the tilted washboard potential, and where now phi would be the coordinate of the particle in this potential. And the tilt of the tilted washboard, that's proportional to the bias current, and as long as that bias current is less than the critical current, there will be these minima in the potential energy where the particle can be trapped. And classically, if the particle is trapped at one of these minima, it can't get over to the other side of that barrier unless you give it enough energy to do so. But by quantum mechanics, it could actually end up on the other side by quantum tunneling. And in this case, this is an example of macroscopic quantum tunneling. Since the electrons in the superconductor, they form sort of a big molecule, so this tunneling of phi from there is like a phase change in the superconductor in the Josephson junction of 2 pi, and we observe that as a voltage spike. Now, the system that we're studying is the Josephson junction coupled to a mechanical resonator, which is basically a piezoelectric crystal which behaves like a simple harmonic oscillator, and we attach that in parallel to the Josephson junction. And the reason we're studying these systems is because these Josephson junction resonator pairs, it's been proposed that they could be used in quantum computing as qubits. And so we need to know how they behave in order to be able to use them. So we could approximate one of the minima of the tilted washboard potential as a parabola. In which case we could imagine that the Josephson junction particle is just a mass on a spring, a simple harmonic oscillator. And when we couple it to the resonator, to the mechanical resonator, that's like putting another spring in between those two blocks. And it's been found in previous research that the energy of the coupling between the two blocks goes like the coordinate of the Josephson junction and the velocity of the mechanical resonator. Now, what we wanted to find is the tunneling rate in the Josephson junction. And so then you can't approximate it as a parabola, in which case there wouldn't be tunneling. So we approximated it as a cubic function, so there's this barrier here which the particle can tunnel through. And so what we wanted to find was this tunneling rate, which is the probability that the particle will tunnel through that barrier in per unit time. And that's equal to an attempt rate, which is basically how often the particle tries to escape from that, from the minimum there, multiplied by the probability that it will tunnel through in one attempt. And in order to include the damping of the environment on the Josephson junction and the resonator, we modeled the environment as two bats of harmonic oscillators, which were each coupled to the junction of the resonator, with different coupling strengths. Now, we used Feynman's passive approach to quantum mechanics and semi-classical perturbation technique to find the tunneling rate of the Josephson junction in the zero temperature limit. And so we found that you could write the tunneling rate in this scaled form where the tunneling rate divided by gamma 0, where gamma 0 is just the tunneling rate when the junction is not coupled to the resonator and when there's no damping. We found that that's equal to a scaled attempt rate times the scaled tunneling probability given by these things S0 and delta S, where S0 is just the classical action of the junction when it's not coupled and when it's not damped. And delta S is the perturbation of that action due to coupling it to the resonator and damping it. And so we found that the delta S can be written in this form, where this term over here is the perturbation due to damping the Josephson junction, and that was found in the 1980s. And this term over here is the one that we calculated, which is the perturbation due to the coupling to the resonator and the damping on the resonator. So then we plotted our results. And so on this plot, we show that the scaled tunneling rate we plotted versus the frequency, scaled frequency of the resonator and the scaled coupling strength to the resonator. And this is the same plot, just a contour plot. So we see that in this corner over here where there's large damping and small resonator frequency, the tunneling rate is very much suppressed. It goes almost all the way down to 0. And we see that the attempt rate actually behaves in the opposite manner. It gets increased in that corner, but the total effect is due to the tunneling probability, which has this exponential limit. And so that wins out. And we also plotted the scale tunneling rate versus the damping on both the junction and on the resonator. And we see that, so if we start up here where there's no damping, as you increase the damping on the Josephson junction, that decreases the tunneling rate, suppresses it even more. And when you increase the damping on the resonator, that decreases the suppression or increases the tunneling rate. And this is the same plot just for a larger value of the coupling to the resonator, so we see that that damping on the resonator has a more pronounced effect. So to understand if these results make any physical sense, we see that if you increase the coupling strength between the junction and the resonator, which that is, you can think of as increasing the stiffness of that spring which was connecting the two blocks. So you would expect that the amplitude of the oscillations of the Josephson junction block would decrease, which that's what this red arrow means. So, and by amplitude, we really mean the average value of phi squared, which you can think of as the width of the wave function of the Josephson junction. And also, as you increase the resonator frequency, that corresponds to decreasing the mass of the resonator of that second block. And so that's like decreasing the inertia, which would also make the oscillations, the amplitude of the oscillations, increase. So that's what this arrow means. And when we damp the Josephson junction, that's like increasing the friction, and so that decreases the amplitude. And when we damp the resonator, when we increase that damping, that reduces the effect of the coupling strength, and so in effect it increases the amplitude of the oscillations. And now in this column we see that the average value of the momentum squared actually has the inverse behavior of the average value of phi squared, and that's due to the uncertainty principle. And the attempt rate, that behaves like the p squared or the speed of the junction, because as the particle is bouncing around in that minimum faster, it attempts to escape more. And the tunneling probability behaves in the same manner as that width of the wave function, because if you decrease the width of that wave function, that means that less of it sort of leaks out past the potential barrier, and it has less probability of tunneling through. And so our main result was that when you couple the Josephson junction to a resonator, that suppresses the tunneling rate, and that's a significant result because it's necessary for the operation of qubits that they have a very small tunneling rate. And the possible extensions of our work is to approximate the tilted Washburn as a cubic function, which is a better approximation, or to add an AC drive force to the Josephson junction to see what happens to the tunneling rate. Thanks.
Okay, any questions for our speaker?
How big a shot is it, roughly, do you know, that when a quantum computer is successfully built, the qubits are going to be these things? Is this a really good candidate, or is it?
I don't know.
That's way up. There are many candidates. But this is one of the more newer proposals.
Other questions?
Again, from the chemistry point of view, I love the quantum theory, and you know, we talk about the wave nature and the particle nature of these atoms that we're studying. So you were concentrating just on that wave, because I mean, I noticed that most of the terms that you use are terms from wave studies, like the amplitudes and those kind of things. I mean, you didn't. I guess I'm asking was there any was there any room for describing the particle nature, or was it simply the wave nature of these materials?
Well, I guess when we were talking about the particle being trapped in that tilted washboard, they weren't, I guess, thinking of it as a particle in one of those minima.
Oh, okay.
That was actually localized somewhere. But then to think about the tunneling, then you have to think about the wave
Then you
nature.
have to go to the wave, yeah. Okay.
I think I have time for one more short question, if we have one. Okay, if not, let's thank our speaker again. Thanks, Josh. And that actually concludes our oral session. Why don't we just go ahead and thank all of our speakers again. It's been a great job. Participating in this oral session. We have a little break now, but very shortly lunch will be served out in the atrium. Thank you again for coming to this session, and we look forward to lunch and a poster session after lunch. Brad, would you like to say anything?
Scheduled to be served ready at noon.
Okay.
So it may not be quite ready yet. We were thinking some people might need some time to put up their posters, but they're so efficient they've already got that done. So we can hang around here and converse out in the atrium, and lunch should be ready in just a few minutes. Then the poster session will start at 1.
I did. Just in case.